Good morning, everyone. Today I'm going to talk about some of the historical roots of literate programming. This is a style of programming introduced by Donald Knuth in the 1980s as he was developing TeX and Metafont. Literate programming is a way for one human to communicate to another human how a computer program works, including the motivations for writing the program, the assumptions made, the general structure of the program, and all the way down to its actual implementation in some programming language. Very roughly, a literate program looks like a big essay with a bunch of prose and some rough sketches of algorithms in something that looks like pseudocode, oftentimes formulas and figures, and some code sprinkled throughout this beautifully typeset essay. Incidentally, a literate program can be compiled into an executable that can be run on a computer, but the human-to-human communication is really the main point. I first learned of literate programming after hearing that Knuth wrote the first the first draft of TeX on pencil and paper, and then debugged it after typing this draft into the computer. I didn't believe it at first. No way. TeX was a large system, and this seemed impossible. I learned from Wikipedia that TeX was written in some language called Web, which was itself a mix of Pascal and TeX? And then that Web itself was written in, and you already know, Web. The mysteries piled up. I had to find out more. And I was soon completely enraptured with this strange paradigm called literate programming. And so the next question was, where in the world did Knuth come up with this marvelous system? As we'll see later, there was a whole host of precursors, but Knuth singled out one as a primary inspiration, the work of a Belgian computer scientist named Pierre Arnoul de Marneffe, entitled Holon Programming, a survey, from 1973. Excellent. I had no clue what a Holon was, and I couldn't wait to find out. So I took the proverbial sip of coffee, fired up my search engine, and waited to be delivered this document called Holon Programming. But there are more things on heaven and earth, Horatio, than are served up in all your internets, and after searching longer than I'd like to admit, I found almost nothing. Every reference to this Holon programming led back to citations by Knuth, or portions that he had mentioned in interviews. A ray of hope shone from the site literateprogramming.com, which contained 3 tantalizing paragraphs from this report, and there wasn't anything else that I could find. So I began my quest to get a hold of this elusive report. I wrote to Professor de Marneffe, and he wrote back. He was happy I was interested in the work and would scan the entire thing and email it to me when his health got better, as he had just had a long stay in the hospital. After some time, I wrote to Knuth, who also kindly responded, saying that he donated his copy to Stanford, but that it seems to have disappeared from their records. All of this, of course, only increased my desire to read de Marneffe's report. Knuth pointed me to the single library in Germany that held this report, and also sent me a letter from 1974 that he wrote to de Marneffe, which is lovely and is reproduced in the Tugboat article. And so, some time passed, but at long last, with the help of librarians in Hanover, Germany, and Lincoln, Nebraska, I was finally able to hold all 135 pages of Holon programming in my trembling hands. But first, let's back up a little bit and talk about the lead up to this elusive report and eventually its contents. To do so, we'll focus on 5 characters: Arthur Koestler, Herbert Simon, Edsger Dijkstra, Don Knuth, and the man of the hour, Pierre Arnoul de Marneffe. We begin our historical investigation by looking at this funny word, Holon. Where did it come from? What does it mean? The word Holon first appears in 1967 in Arthur Koestler's book, The Ghost in the Machine. Koestler was a Hungarian author and journalist who wrote many works, most of which were in English. The Ghost in the Machine begins with Koestler vigorously denouncing behaviorist psychologists who claimed that all animal behavior, including human language and consciousness, could be explained by simple chains of stimuli and responses. These are called stimulus-response chains, or SR chains for short, and they can be depicted like this. A simple example including one stimulus and one response would be someone first touching a hot stove and then responding by quickly pulling their hand away. But when it came to modeling human thought processes and other complex biological systems, Koestler said, "Are you kidding me? This chain depiction is laughably inadequate." Instead of a chain, Koestler says that biological systems are hierarchically ordered and are better represented by an inverted tree, branching downward, like this. Koestler uses this tree to discuss how an imagined lecturer might prepare an upcoming speech by starting with a vague idea up at the top level, or the root of the tree, and then, and here I'm quoting Koestler, at each node or branching point of the growing tree, more details are filled in. And Koestler continues, saying there is a, quote, stepwise elaboration, articulation, concretization of originally inarticulate, generalized intents, end quote. Now, if this upside-down tree and talk of nodes and branch points and stepwise elaboration seems awfully like computer science lingo, that's because Koestler took it all from Herbert A. Simon, a polymath who made fundamental contributions to computer science, theorizing about complex systems, programming languages, artificial intelligence, and general methods for problem solving. One of Simon's ideas that's relevant to our discussion is his computer program from 1957 called the General Problem Solver. Remember this phrase. This was co-authored with Newell and Shaw. So Simon, just like Koestler, talks about problems being solved by breaking a big task into a bunch of related subtasks, and if you are able to complete the subtasks, then the problem will be solved. We won't spend much more time on Simon, but I just want to note that his language and metaphors were used heavily in Koestler's development of the Holon. So, as a basic example, let's look at a nice, boring task, getting a drink of water. This task could be broken up into the subtasks of finding a water source, finding a cup, filling the cup, and then drinking from the cup. And these can be further broken down into smaller subtasks if we wanted. Each of these subtasks can be considered as its own separate problem, but they can also be viewed as embedded within the overall context of our initial goal of getting some water. So when Koestler introduces the word Holon in chapter 3, he's citing Simon left and right, and this new word is already intimately associated with computers. Let's look at his definition of Holon. It seems preferable to coin a new term to designate these nodes on the hierarchic tree, which behave partly as wholes or wholly as parts, according to the way you look at them. The term I would propose is holon, from the Greek holos, meaning whole, with the suffix on, which, as in proton or neutron, suggests a particle or a part. The main point is that each holon, or node, can be understood all by itself as a mostly self-contained unit, or it can be considered as a part of a bigger picture, depending on the desired level of abstraction at any given time. Okay, that's all for Koestler, who is the most cited author in de Marneffe's report. Now I'm going to drink some water. No cup. The second most cited author is Edsger Dijkstra. Dijkstra was a Dutch computer scientist who made seminal contributions in algorithms, program correctness, programming paradigms, etc., etc. Dijkstra is a giant in the field. A few years after Kessler published The Ghost in the Machine, Dijkstra circulated a report entitled Notes on Structured Programming. Its impact in the programming community was massive. Dijkstra said that humans are pretty dull creatures with a woefully short memory, so if we ever hope to make a computer program do what we intend, we need a bunch of guardrails and structures to help our tiny little brains out. Some of these guardrails include the systematic use of just a few now familiar control structures, including if-else statements and while loops. But today we're interested in Dijkstra's approach to developing programs, which he calls stepwise program composition. He says, quote, "The basic pattern of my approach will be to compose the program in minute steps, deciding each time as little as possible. As the program analysis proceeds, so does the further refinement of my program." End quote. Dijkstra gives each of these steps an abstract name and encourages us to use the name on account of what it does, while disregarding for the moment the details of how it works. He calls this kind of program a layered hierarchy of machines, corresponding to different levels of abstraction. He goes on to say that, quote, "Each program layer is to be understood all by itself," end quote. Let's see an example. Dijkstra wants to write a program to print the first 1,000 prime numbers. So that's the first layer. To do that, we decompose this high-level task into two subtasks. Fill a table with the first 1,000 prime numbers, and then print this table. And he goes on decomposing the problem into smaller and smaller subtasks. Both Dijkstra's language and approach are quite similar to Kessler's problem-solving tree of Holon's. Incidentally, this prime number program is also the problem Knuth uses in his 1984 literate programming paper. When we get to section 13 in Dijkstra's notes, which describes his second example of stepwise program composition, he does something incredible. He gets tantalizingly close to literate programming, designing a program with loads of prose, interspersed with small computation chunks that are given short English descriptors, whose code could be extracted to form an algol-like program. But then, Dijkstra turns away from his handiwork, indifferent, paring his fingernails, saying, quote, "Whatever I shall develop, it will not be a general problem solver." Note the Herbert Simon reference here. "Not a mechanical one, not even one written for the benefit of the human solver," end quote. And indeed, like Moses, Dijkstra doesn't cross the River Jordan, but eyes it from afar, eventually ceasing to program entirely in his later decades. But I'm not disparaging this path. I suppose it's somewhat like the Zen swordsmanship tradition of winning without a sword. I should note that Dijkstra would loathe my connecting him just now with not one, but two religious references, but I couldn't help myself. To describe his hierarchy of machines, Dijkstra uses the metaphor of a necklace strung from individual pearls. This is not a useful metaphor. Unlike Dijkstra's Russian doll-like machines within machines, pearls do not contain other pearls. Secondly, one thinks of connecting a necklace back onto itself, into a circle. And certainly not all programs are a continuous loop. And finally, just now, one thinks of the stimulus response chains that Kessler found so unhelpful in describing complex systems. So, what is a better metaphor? De Marneffe said, "But of course, it's the Holon." And let us turn now to de Marneffe's report. De Marneffe was correcting more than just a clumsy metaphor. His main critique of how he saw structured programming being used comes in the first chapter of his report. Quote, "The programmer cannot use the same language for the design and the implementation of a program. When all the levels are defined, the programmer must undertake the mapping of the designed program into an executable one, a non-trivial and an error-prone operation." End quote. Another critique was that there is no suitable tool for implementing each new semantic level, meaning once a programmer has decomposed a program into tiny subproblems, they will not want to stuff each subproblem into a procedure because of efficiency concerns with procedure overhead. This led to programmers structuring each level in huge steps, and this takes away the whole power of Dijkstra's stepwise refinement. Okay, I've been rambling for way too long now. As Knuth suggests in his letter to de Marneffe, a Holon program is mostly self-explanatory, so just show an example right away. The example program in de Marneffe's report is a solution to a problem Dijkstra poses in section 16 of his notes. The problem is essentially to take a sentence, reverse every other word, and remove extra spaces, but the details aren't really relevant here. So, without further ado, this is what a portion of a Holon program looks like. Each of these 3 units is a separate Holon. A Holon is named by giving it a unique prose descriptor of the subtask to be done. For example, the 3rd Holon here is named read first symbol. The Holons can be written in any order, though in de Marneffe's example, it's purely top-down, meaning he starts with the most general task and proceeds methodically to flesh out each successive subtask. Within the Holons, the bold words are algol-like keywords describing control and block structures, such as loops and declarations. And low-level algol statements are bracketed between pound symbols, as shown in the 3rd Holon's assignment statement, LRS gets RNC. The ETC keyword in the 2nd Holon abbreviates unambiguous prefixes, so that you don't have to write out the entire phrase, find first word starting character, every time it appears in the source of your program. I'm still struck by how pleasant de Marneffe's program is to read. It's just like pseudocode. See how digestible each little Holon is? It's a wonderful demonstration of Dijkstra's stepwise program composition. And the real kicker is, de Marneffe describes a synthesizer akin to Webb's Tangle program that will expand each of these Holons, just like a macro, so that the final product is a well-formed algol program, pictured on the right. You get beautiful documentation and can make an executable from a single source file. This insight of de Marneffe's is just brilliant. Now for comparison, let's look at what the equivalent fragments would look like in Knuth's web language. I know this is too much text to absorb at once, but I just want to point out that apart from the different mechanisms used to declare global variables in Web and the cross-referencing aids given by Web, the 2 languages look strikingly similar. Let's look at the 2nd Holon, corresponding to Webb's section number 2. Knuth surrounds his section names with brackets and uses cross-referencing, but otherwise, these 2 are twins. It's not shown here, but de Marneffe also describes the change command, which works almost the same as the change file mechanism in Web. There's a text keyword that can act like the prose sections in Web. There's the synthesize command I mentioned that acts like tangle, and there's an output command that acts like a primitive weave. But that's a bit of a stretch because there was no automatic typesetting in these early days. One of my favorite oddities in de Marneffe's report is the suggestion that with his system, programs can be written largely with ideograms, that is, small pictures symbolizing some concept. He takes this idea from way back, from Charles Babbage in the 1800s. And in fact, there now are esoteric programming languages that do just that, namely one called emoji, where you write a program almost entirely with a fixed set of emojis. Other parts of de Marneffe's report discuss an early form of contract-based programming akin to the Eiffel programming language, and de Marnef even outlines a full-blown operating system based around the Holon concept. But I'm getting off track. So what exactly did Knuth add to all of this spade work done by de Marnef? Well, it turns out Knuth added quite a lot. First of all, Knuth actually coded up the first literate programming implementation. De Marnef planned on doing so with HPL, or the Holon Programming Language, but as far as I know, this never happened. Not only did Knuth develop a working literate programming framework in Web, but he used it to create the first proofs that this approach actually works, and works really well, namely the programs for TeX and Metafont. Secondly, Knuth made the essential design decision to bring the prose to the forefront and to regard the program as an essay with interspersed code. The value of informal explanations, explaining design decisions not taken, adding metaphors, giving motivating examples. If you want someone else to understand a large program, these things are absolutely crucial. What else? Well, the list is long and time is short, so I'll just give a quick enumeration. Knuth typesets the code and doesn't hide it between ugly pound symbol delimiters. He adds cross-referencing, tables of contents, indices, mini-indices, appendices, bibliographies, figures, etc., etc. He brought all wonderful devices from the ancient art of literature and bookmaking to bear on composing an intelligible computer program. I want to pause to point out that influence can be a very slippery thing. I've been making the case that Simon influenced Kessler, and both Kessler and Dijkstra influenced de Marnef, and that de Marnef then influenced Knuth. And this is true to a certain extent. But as Bob Dylan says, reality has always had too many heads. And it turns out that Knuth, too, was an influence on de Marnef. Knuth had been thinking about combining excellent documentation with source code long before he received de Marnef's report. In a paper from 1963, Computer-Drawn Flowcharts, Knuth opens with the sentence, "Perhaps the greatest problem in computing today, although little has been written about it, is the need for better documentation." He goes on to describe a system to write programs that include 3 levels of documentation: a formal language, a flow outline, and a flow chart, in increasing order of abstraction and generality, that provides efficient person-to-person communication of algorithms. This system has automatically generated complete cross-referencing, like in Web. Knuth also writes in this paper that, quote, "Each section usually begins with a description of its general function and some of the assumptions made. At the close of each section, another explanatory paragraph often appears, in order to clarify the more important coding details." End quote. And like de Marnef, Knuth wrote his own response to Dijkstra's notes, in which he composes a program out of small code sections, not exceeding 8 lines, each labeled with a natural language descriptor, constructed in the order in which decisions were made, and systematically expanded and interleaved into a machine-readable form. De Marnef cites this very example from Knuth in his Holon Programming report. This is all to say, any neat and proper idea of influence seems in the end to be a happily tangled mess. There are so many other names to mention that were important precursors to Knuth's literate programming, many of which are listed in the Tugboat article. I especially want to point out the work of Peter Nauer and highly recommend his paper, Formalization in Program Development, from 1982, where he stresses how informal explanations are crucial to help others comprehend a large program. It calls to mind a Blaise Pascal aphorism that all of our reasoning reduces itself to a yielding to feeling. And one more Peter Nauer plug. His typesetting work for Algol programs, done in collaboration with executive editor for ACM, Myrtle Kellington, was huge in letting us see how beautiful source code listings could be. I'm excited to say that thanks to Carl Berry and Barbara Beaton, Many of these precursors will soon be published through TUG in a slim anthology entitled Pre-Literate Programming. It's going to be a fun historical romp. One last thing. Demarneff's entire report is now typeset, and it's freely available at this address. So please check it out. Thanks Don and Carl for encouraging me in this project, and thanks to you all for listening to me yammer on this morning.
Thanks, Mike. Are there any questions? None?
So not really a question, but a comment. Dijkstra was a very interesting character. He left the Netherlands, I think, in the early 70s and moved to the University of Texas. Sorry, the College Station campus of Texas A&M University, where he remained the rest of his life. And he wrote a lot. Everywhere he went, he wrote a report on his trips. And all of his writing was done with a fountain pen, including his software. And that software was almost never put into a computer. He was so confident it was correct. If you search for Dijkstra BibNet, you can find a complete bibliography of his works online with everything he wrote has been collected by the university and put into an archive. So it's all freely available, and it's very interesting to read.
Great, thank you. I will definitely check that out.
Any other questions? Yes?
Thank you for your talk. It was really fascinating, and I'm going to look to Holon Programming report. Most of your examples were about imperative programming style of coding, including Knuth and the like. And it's kind of better, or how to say, the declarative way of stating the states of the program or stating the reality that is modeled by program is kind of better or better understandable. So I wonder whether in your studies weren't some notions of this approach of describing things that might be automatically derived into working programs. So that's...
Yeah, so in my, the old documents I've looked at have described a purely imperative style. Personally, when I have programmed with functional languages, not something like Prolog, but something like Haskell. And it is in a literate style, and it's a very different approach than kind of diving very deep into very nested structures like you would do in C Web or Web. So I don't have a good response about how one would use Demarneff and Knuth's approach in a better way in a functional language, purely functional language like Haskell. But I do know that Knuth has somewhat recently said that out of the hundreds of programs that he writes each year, maybe 4 or 5 could be improved by not being written in an imperative style. So I don't know how he would respond to this. But.
Thank you.
Thanks. This is a response to your response and to your question. I think that the need for literate programming is tightly bound to the level of abstraction of the programming language you use, but also to the level of expressiveness it has. And you're completely correct in saying that functional programming or object-oriented programming, for instance, bring new levels of expressiveness in the language, and I think it reduces the need for literate programming, because literate programming is a way of organizing your thought around the complexity of something which is not directly expressible in imperative languages. And so if you had programming paradigms in your way of writing your programs, your thought is more directly expressed in the language itself. And I think it behaves exactly like design patterns for object orientation. The need for design patterns is not because the application domain is complicated. It's only because the object-oriented language that you use is unable to express it as directly as you would like it to be. So it appears that when you use different kinds of object orientation, such as prototype programming or more extensive object orientation in dynamic languages, the need for design pattern completely disappears because the design patterns are embedded in the language itself. And so my conviction is that the need for literate programming is more embedded into a lack of expressivity in imperative programming style than other more modern way of writing programs.
Thanks.
So, Mike, I think we're done with the questions now. Thank you very much. And we move on to the next speaker.